Energetics. The first part of energetics will be looking at thermochemical equations and the various definitions. So for thermochemical equations, remember that it's important to list the state symbol, as the state symbol will affect the value of the enthalpy of elements or compounds. Next, it's important to note that the stoichiometric constant of the equation will also affect its enthalpy change. And the basis of all the enthalpy value sits on the fact that the enthalpies of elements in their standard states, which is at 298 Kelvin and 1 bar, is 0. It means that the enthalpy of oxygen gas, O2 gas, N2 gas, Cl2 gas, I2 solid are all zeros. Let us now run through the 11 enthalpy change that you need to know. The first one is the enthalpy change of formation. The standard enthalpy change of formation is to produce 1 mole of the compound from its elements under the standard conditions of 25 degrees Celsius and 1 bar. The more negative the standard enthalpy change of formation, the more stable the compound is. Next, we'll be looking at the standard enthalpy change of combustion. Standard enthalpy change of combustion is when you take 1 mole of a substance and completely burn them in excess oxygen under standard conditions, 25 degrees, 298 Kelvin, and 1 bar. Next, we have the standard enthalpy change of atomization. For the standard enthalpy change of atomization is to produce 1 mole of free gaseous atoms from an element or compound. In the case of the standard enthalpy change of atomization of carbon, you will find that it is the energy required to break the strong covalent bond between carbon atoms in a graphite giant molecular lattice structure. In the case of standard enthalpy change of atomization of sodium, you'll be looking at the breaking of the strong metallic bond. In the case of the atomization of hydrogen gas, you'll be breaking the single H2H covalent bond. And finally, for the atomization of oxygen, you'll be breaking the O-to-O double bond. Bond energy is next. Bond energy is defined as the average value of the gas phase bond dissociation energy. So what is bond dissociation energy? Bond dissociation energy is the standard enthalpy change when per mole of a specific covalent bond is cleaved by homolysis in a specific gaseous reactant to produce gaseous product. Hence, it's important to note that when you deal with bond dissociation energy or bond energy, both the reactant and the product must all be in gaseous form. So the difference between bond energy and bond dissociation energy is that bond energy is the average value. Therefore, bond energy is less accurate. While in the case of bond dissociation energy, it is specific to the covalent bond. And in the example illustrated in methane, the C2H bond that you break is different from the second C2H bond that you break. And actually BDE2 will be higher than BDE1. So these are the various bond energy that's actually found in your data booklet. Do note that there is actually a C double bond O specifically for carbon dioxide. And this C double bond O is generic, which means it can be applied to structure, like for example, your methanol. And finally, you also have a specific value for benzene. So in the case of benzene, when you break the bond between the carbon atom, that's the value that you ought to be using. Lattice energy. Lattice energy is the heat energy evolved when 1 mole of crystalline solid is formed from its gaseous ions under standard conditions. So this will be the equation to represent the lattice energy. Next we have is the first ionization energy. So that's the equation. And obviously you have the second IE and the third IE. Next we have the first EA. Do take note that the first EA is the enthalpy change or is the energy change with the formation of 1 mole of gaseous anion with charge of -1 from 1 mole of gaseous atom by taking in 1 mole of electrons, as illustrated in this equation. So the first EA would be negative for non-metal, and the second EA would be positive. So second EA is when 1 mole of X minus accept 1 mole of electrons to produce 1 mole of X2 minus gas, X2 minus. And both X minus and X2 minus are in gaseous state. With that, let's take a look at the bond-Haber cycle for sodium chloride. In the bond-Haber cycle for sodium chloride, it's important to note that it's not possible for us to experimentally derive the value for lattice energy of sodium chloride. The reason is because Na plus and Cl minus are in the plasma state and they are actually not stable. It cannot be held separately in reacting vessels for chemical reactions. However, in the case of enthalpy change of formation of sodium chloride, that could be a value that could be derived experimentally by reacting sodium in excess chlorine. in part 2, we'll show you how we can make use of a calorimeter to derive the values of such enthalpies. So once one is derived, we can make use of a series of known values of enthalpy of atomization, or bond energy, or ionization energy, and also electron affinity. So in this case, the value of 2, 3, 4, and 5 are known. So by drawing the Born-Haber cycle, we are able to derive the value of the lattice energy, since the magnitude of the enthalpy change for 5 and 6 must add together to be equal to 1, 2, 3, and 4. Let's take a look at another Born-Haber cycle. In this Born-Haber cycle, we're studying the lattice energy for sodium oxide. And in this case, we can atomize sodium and we need to multiply by 2. And in the case of atomization of oxygen, we just multiply by 1, since there's only 1 mole of gaseous atom form, as compared to sodium, which has 2 moles of gaseous atom. Or in this step, we can make use of half of bond energy of O double bond O. The reason is because when you cleave a O double bond O, you ought to get 2 oxygen, but in this case, we only need 1 gaseous oxygen atom. Finally, for 2A to become 2A, 2Na plus and 2E, we will have 2 times the first IE for sodium. And here we will have the first EA for oxygen, where oxygen accepts 1 mole of electron to form the O minus. So remember, when we actually discuss first EA of non-metals, they are essentially negative in value. Then in the second EA, when the O minus accepts the second electron, to form O2 minus, that second EA is positive. And it's important to note that the first EA plus the second EA is also more than 0, which is the reason why the energy level of this is higher than this. Let's resume looking at the last 3 definitions of enthalpy change. The first one is the standard enthalpy change of hydration. Standard enthalpy change of hydration of a gaseous ion is the enthalpy change when 1 mole of gaseous ion is dissolved in large amount of water under standard conditions, again of 25 degrees Celsius, 1 bar. So in a nutshell, enthalpy of hydration is in actual fact exothermic and is directly proportional to the charge density of the cation or anion. So a good example to look at is that F minus, which has the smallest anionic radius, will actually have the highest charge density. Conversely, I minus, which has the largest anionic radius, will have the lower charge density, and hence we can conclude to say that the standard enthalpy change of hydration of F minus will be more exothermic than I minus. Next, we have the enthalpy change of dissolution or solution. And it's defined as the enthalpy change when 1 mole of substance dissolved in excess solvent to make an infinite dilute solution under standard conditions, again of 25 degrees Celsius and 1 bar. If the enthalpy change of solution is negative, then the substance is soluble in water. If the enthalpy change is positive and the value of the enthalpy change of solution is small, then it is possible that the substance can still dissolve in water. So for example, like sodium chloride, which actually has an enthalpy change of 4 kilojoules per mole. When sodium chloride dissolves in water to form aqueous ion, we could also see it in another way, which is that the ionic bonds in the lattice energy need to be overcome and broken. So that's the reason why we have your negative lattice energy. After the ionic bonds have been overcome, you would have produced separated gaseous ion. The separated gaseous ion can then be hydrated with water molecules to form aqueous ions. Hence, the enthalpy of solution is equal to the negative value of the lattice energy plus the hydration energy of the cation and anion. From chemical bonding perspective, when the compound actually dissolves, we are breaking the ionic bonds. Thereafter, the gaseous ion form ion dipole attraction force. For a compound that's very soluble, the ion dipole attraction force will release sufficient energy to overcome the ionic bonds. Poor solubility means that the ionic bond will be extremely strong, which means that the magnitude of the lattice energy is extremely high. We now look at the final definition, which is the enthalpy change of neutralization. So the standard enthalpy change of neutralization is defined as the enthalpy change when 1 mole of water is formed in the neutralization between an acid and alkaline in aqueous solution under, again, standard conditions of 25 degrees Celsius and 1 bar. So in this case, when you take nitric acid to either neutralize with sodium hydroxide or barium hydroxide, since all the compounds here are strong acid and strong alkaline, so the H plus and O minus will come together to neutralize each other to form water molecule. Hence, the enthalpy of neutralization are both negative 57 kilojoules per mole. Similarly, in the same case of sulfuric acid with KOH, in the standard enthalpy of neutralization will still remain as negative 57 kilojoules for every 1 mole of water molecule formed. In this thermochemical equation, we have 2 moles of water formed. That's the reason why the enthalpy change is 2 times negative 57 kilojoules. We now take a look at what happened when either the acid or alkaline is weak. Say, for example, in this case, we take a weak acid. So in the case of a weak acid, not all its molecules is fully dissociated. And the main part of the molecules remains as CH3COOH. Hence, energy need to be taken in as enthalpy of dissociation of the weak acid to form CH3CO- and H+ before they could actually undertake the neutralization reaction to produce water molecule. And that enthalpy of neutralization remains as negative 57 kilojoules per mole. The enthalpy of dissociation will be endothermic, since energy is taken in to break the molecules to form ions. Hence, the enthalpy of neutralization between the strong alkaline and the weak acid would actually be less exothermic than negative 57 kilojoules per mole.